Hello guys. So last time we were doing this paper, Unit 3, Edexcel, International A levels. So we did the first three questions and today we're going to move on to the fourth question. So let's see what the fourth question is about. Yes, so let's start. It says a student made measurements on a length of metal wire. The student used a micrometer screw gauge to measure the diameter D of the wire. The student recorded a single measurement of D as 0.27 millimeters. Determine the percentage uncertainty in this measurement. So we have to find the percentage uncertainty. Now, as you remember in the last video, if you watched that, we discussed about how to find percentage uncertainty. So it was about like if you're finding percentage uncertainty, one formula is that you have to know the absolute uncertainty. You divide that by the mean value, which is basically your measure value, times 100%. Okay, that's one of the formulas. Another formula was like, if you're not provided, like what is the absolute uncertainty? The absolute uncertainty is, for example, if you were told that the measurement is 0.27 plus minus 0.01, then this would be like in that case your absolute uncertainty. This is just an example, okay, not related to the question. Um, Now, another case is when you're given a range of values, like you're told several values, like 0.27, 0.28, 0.29, 0.26, and you're asked to find the percentage uncertainty. In that case, the absolute uncertainty is just the range divided by 2. Range is highest value minus lowest value, so that would be 0.29 minus 0.26 divided by 2. And the mean value would just be the mean of these four values. This is the second one. And the third case is what we're dealing with right now, where they just told us a single measurement, which is basically the mean value, and they've asked us to calculate the percentage uncertainty. So the now let's go back to the formula. The formula is percentage uncertainty equals absolute uncertainty over mean value divided by over mean value times 100%, right? That is a formula. Now we know the mean value is just 0.27 because that is the measured value. Then what is the absolute uncertainty? We know the measuring instrument is a micrometer screw gauge, which is a very well-known instrument, and its least count, the smallest value that it can measure, is 0.01 millimeters, right? That is its least count. For vernier calipers, that is 0.1 millimeters. But for a micrometer screw gauge, it's 0.01 millimeters. But that is not the absolute uncertainty. Since it's an analog measuring device, you will divide that by 2. The absolute uncertainty for an analog device is an analog device is where you have to take the reading instead of it just showing you the final value on a screen. So you have to divide that by 2. So it would be 0.01 over 2 divided by 0.27 times 100%. So that would give you 1.85%. So that's the percentage uncertainty in the screw gauge. So remember, whenever you do any past paper question, relate it to questions of other, like similar questions from other papers. Like over here, this is a question specific to micrometer, but it could appear for so many other analog devices. It could appear for a meter rule, uh, and other vernier calipers. So if it were for a meter rule, the the smallest reading a meter rule can measure is 1 centimeter. So you would divide that by 2, and then divide by the mean value and times 100%. Okay, so this is how you solve it, right? Let's move on to part B, part II. Sorry, the student repeated the measurement of D at different positions and orientations and calculated the mean. Explain another technique she should use to determine an accurate value for D. Um, Normally, when they ask you about an accurate value of something, the first thing that comes to your mind, like that should always come to your mind, is to repeat the readings, calculate the mean. But this student already did that. So you have to think of another thing. Whenever you're dealing with devices like micrometer, vernier calipers, balance, etc. Uh, in all these cases, there can be a zero error in the system, right? It's natural. So, to get an accurate value for any question that involves micrometer or vernier calipers, unless they've already mentioned that, you can always explain about the zero error. So they talked about getting an accurate value. So what the student can do, the student can measure the zero error. What is the zero error? So it's when the zeros are not aligned on the two scales of the micrometer. They're not aligned on, and because of that, when you like make a measurement, it's either going to be larger than the exact value or a bit smaller than that. So there will be an error. Any measurement you will take will be either larger or smaller. So what you have to do, you measure the zero error before measuring the actual length that you're trying to measure. And then at the end, you subtract or add it to your final value, depending on the situation. So the student can measure the zero error, and then so the student can measure the zero error and remove it from the final. We can say correct it in the final measurement. And how will this help? How is this related to accuracy? A zero error introduces systematic uncertainties in the system. How? Because all your values are now greater by a certain amount or smaller by a certain amount. It's not random. It was present in the system and it will cause a deviation in all your values. So, such an error is systematic error. On the other hand, if a random error is something that will cause like outliers, like one value is too large or too small than the rest of the values. So you correct it in the final measurement. This will reduce on the systematic error, providing you with an accurate value for diameter. Okay, next part, B. We've got a circuit over here now. The student formed the wire into a loop. She used the circuit below to determine the resistance between 2 points, X and Y, on the loop. Explain why the fixed resistor is included in the circuit. Okay, so what's happening? We've got a battery connected to an ammeter. We've got a voltmeter and a fixed resistor. We have this metal wire, the same one that we measured the diameter of. And we have to we are trying to find the resistance between the points X and Y on the wire, right? So there's a movable contact here. You can shift it. When you'll change the length, the resistance will change. So there's a voltmeter. The voltmeter will measure the voltage of that part, and then you can find resistance from there. Now, over here, the question is not about resistance. It's not about how to measure the resistance. It's about why the fixed resistor is included in the circuit. Like, why is there this resistor? Okay, so we need you can say that we need the voltmeter to get the voltage. We need the ammeter to get the current. Uh, we can use R equals V over I. But why do we need this fixed resistor? What if we remove it from the circuit? What would happen? So we use resistors in any circuit. The basic purpose of a resistor is to control the current. You don't want current to exceed a certain value. You don't want your circuit to get too hot that there is to get too hot or something to burn, like some device to burn. You don't want the current to become so much that there's a short circuit. Okay? You don't want that. So for that purpose, you use resistors. So the resistors are used in a variety of electrical and electronic devices. Um, for example, any device that works on, like if you can adjust it. Like for example, a fan whose speed you can adjust. So you can do that via a resistor as well. A high resistance will limit the current, reducing the speed of the fan. A low resistance will allow more current, increasing the speed of the fan. So there's no fan here. That was just an example, but over here we are just using the resistor to control the current. So it is there to control the current. Now, it's 2 marks. Always look at the marks, please. That's very important. So you write this line, you get just 1 point for that. So it's there to control the current. And what would happen if it's not there? So otherwise, there can be a short circuit. Something can burn in like the ammeter. If there's a large current and passes through the ammeter will malfunction. So otherwise, there will be a short circuit. That's why in every single circuit you'll see, it will always have a resistor for the same purpose to control the current. Part C. Using the circuit in B, the student investigated how the resistance R between the points X and Y varied with the length L. The relationship between R and L is given, where K is a constant, rho is the resistivity of the metal, A is the cross-sectional area of the wire. Explain how a graph of R over L against L can be used to determine the value of rho. Rho is the resistivity. Um, what is the student doing? They are investigating how resistance of the metal wire between points X and Y, how that resistance changes with length. If you increase length, what will happen to resistance? If you decrease length, what happens to resistance? And we are provided with an equation. And we have to think that if there's a graph plotted between R, a graph of R over L against L, whenever you see something like this, like for example, this is the same thing as Y against X. The first thing is to be plotted on the y-axis, right? R over L against L means Y against X. So you will plot R over L on the y-axis and L on the x-axis. And you have to think how you can find the value of resistivity for that. Any such question in Unit 3 can be answered using the equation of a slope, or the equation of a straight line, the slope equation, y equals mx plus c. Because this equation tells you how y and x are related, what is the slope, what is the y-intercept. So let's compare different things over here. Y here corresponds to R over L as the thing that you are plotted on the y-axis. X is the length. You're plotting the length on the x-axis. M is the slope. So the slope here is not just k, it's minus k. And the y-intercept, C over here is the y-intercept. What is the y-intercept? It is the point on the y-axis where the graph touches it. So like, let's say if the graph looked like this. So this point over here would be the y-intercept. This one is the point where the graph touches it. So y-intercept is equal to what? It is equal to resistivity over area. So this thing, you will mention it over here. So comparing the equation, the given equation to y equals mx plus c, we find out that the y-intercept is what? It is the C thing, which is resistivity over area. So how will we find? Now you won't just stop at this. Remember to answer everything they asked. They asked how do you find the resistivity? The resistivity would just be y-intercept times area. So you will find the area of the metal wire multiplied by the y-intercept from the graph, and you will get the resistivity. Okay, next question. The student recorded the following data. Complete the table with the corresponding values of R over L. Okay. In the table, we have length in meters, current in amps, voltage in volts, and R over L. Resistance over length, so it would be ohms per meter. The resistance is just voltage over current. And we have to find R over L, so we will be finding voltage over current over length. So let's do it for the first one. 1.40 divided by 0.720 divided by 0.1. So in essence, you'll be dividing this by this, and then the whole thing by this. So for the first one, I get, V over I divided by L, right? So I get 19.444. Now, what should I write? Should I just write 19.44? No. Remember significant figures. They should never escape your mind while you're doing any calculations. So what's the rule for significant figures? Your final answer should have, like when you're multiplying and dividing things, like over here, it's just multiplication and division, a division, basically. So the rule is that your final answer should have the least number of significant figures as your data. So if we see over here, this has 3 significant figures because zeros to the right of a decimal point are significant. This has just 3 significant figures, these ones. The one on the left, 0 on the left of the decimal, it is not significant. Then this one, again 3. 0 to the left is not significant. So they're all 3, so your final answer should have 3 significant figures, 19.4. If let's say if one of these was 2, then your answer should have 2 significant figures. If one of these was 1, your answer should have 1 significant figure. Your final answer should have the least number of significant figures as in your data. Okay, the second one, 1.39 divided by 0.390, and that divided by 0.2. So you get 17.82. Again, there are 3 significant figures, so it would just be 17.8. Then 1.42 divided by 0.29 divided by 0.3. 16.32, 3 significant figures, so 16.3. 1.48 divided by 0.250 divided by 0.4. 14.8 is the answer, and again, there are 3 significant figures in each one of these. 1.47 divided by 0.220 divided by 0.5. 13.4. 3 significant figures. I'm getting 13.36, right? So I'll round off the last number, so it would be 13.4. 1.47 divided by 0.210 divided by 0.6. 11.7. It was 11.66 recurring. So I just rounded off. So it's 11.7 for 3 significant figures. So that's R over L. Right. Next part is plot a graph of R over L on the y-axis against L on the x-axis on the grid opposite. So let's do that. Right, so here we've got the graph. Before plotting any graph, you should always be careful that your graph, most of it, half of it, should not be more than half of it, more than half of it should not be empty. Okay, you have to choose a wise scale. So let's begin. Okay, right, just a second. Right, so let's draw the x-axis. Here we've got the x-axis, and let's draw the y-axis now. Here we got the y-axis. Remember to always label your axis. That's very important. Don't just leave it like that. So on the x-axis, what do we have? We have length. Yes, we have length on the x-axis, and that would be in meters. Remember to mention the units as well. On the y-axis, we have R over L. That would be ohms per meter. Units are necessary. Now, let's choose a scale. So length starts from 0.1. There's just an increment of 0.1 and it ends at 0.6. So that's simple. That's already figured out. What about R over L? The least value is 11.7. The highest value is 19.4. Now, let's put down the values of L over here, 0.1, 0, 0, 0.2, 0, 0, 0.3, 0, 0, 0.4, 0, 0, 0.5, 0, 0, and 0.6, 0, 0. I'll just extend this line up till here. Now R over L, if I think about a scale, because it's just between 11 and 20, and I say like, let's take a scale of 12, 14, 18, 16, 18, 20. Then to do that, I would have to start, if I start from 0, it would be 2, 4, 6, 8. And the values that I require, they would even go beyond the graph. So shall I choose a scale of 5? Like just put 5, 10, 15, 20? Again, not convenient because my entire graph would just be lying in these blocks. Right. So what do? I need to choose a sensible scale. And that means when your values are like this, then remember, it's not necessary to start your graph at 0. What you will do, your x-axis starts at 0, but your y-axis, it can start from 11. You can put 11 here. Remember to label it properly. So it's 11. This is, then we have 12, 13, 14. We can go all the way up till 20. So I was saying that we could go all the way up till 20, and that would like take about 9 boxes because we're starting from 11. We could have chosen 12, 14, 16, 18, 20, but we've got 6 values and that would just take 5 boxes. So we can just go all the way um up till 20. So 13, 14, 15, 16, 17, 18, 19, and 20. Okay, guys, somewhere my graph might not look very neat because I'm drawing in a screen. So you need to make sure that your graph looks really neat. All the points, they should be carefully mentioned. It shouldn't be rough. Right, so let's start with the first point. that is 11.7 and it corresponds to 0.6. So it's the scale is quite simple. So it would just be this line, the third line from below 12. So this one, that will be our first point. Then we have 13.4 corresponds to 0.5. So that would be this one. Then we have 14.8. That corresponds to this one for 0.4. Then 13, and then 16.3. 16.33 lines, 3. So that's above 0.3. And 17.8, that's for 0.2. Where is that? Yeah, over here. And the last one is 19.4, that's for 0.1. So 19.4 is this. That was an easier graph to plot. And you can see, we can already see this. It's a beautiful graph. Not in the way that I've written things, but it's covering more than half of the region. The scale is sensible, so it's great. Let's just draw the best fit line. Remember to passing through most of the points in our way. So we can do this. Wait. Again, my line might not be very accurate because I don't have much precision here. So that one, although I think I could just adjust it. I think I should move it slightly to the left. Or it's fine. Okay. So now we got this graph and we have to find the next part is determine the value of k from the graph. Um okay. So how do we find k from the graph? Now, if you remember back above, if I change the position, my graph will change. Okay, it's okay because I was annotating. Right, so over here you can see that where there's the equation, this part I'm talking about. So we said that the slope is minus k. So they're asking find the value of k from the graph. Slope is minus k. So essentially what we have to do is we have to find the slope, multiply it by a negative sign, and we're good to go. So slope equals minus k. So k is the negative slope. Let's find the slope. We'll choose any 2 points from the graph. Since the points perfectly correlate, so this would be negative of what? What is the slope formula, by the way? Slope is just y2 minus y1 over x2 minus x1, right? That is the formula of slope. You choose 2 points on the graph on the y-axis and like 2 points. Mention the y-coordinates and x-coordinates and subtract those. That's the slope. Let's find it y2 minus y1. We can choose just the endpoints. So 19.4 minus 11.7 over 0.1 minus 0.6. So this point we are choosing, that is 19.4 comma 0.1. I should label it as xy, sorry. So 0.100 and 19.4. And this point, which is, okay, I've just realized I left a point down there. My bad. Let me just correct that. So this line, it should have been drawn further, like this. Yeah, that's fine. Um, Again, when you're drawing it on a paper, it's much better. Right, so we've got 19.4, 0.11 as the first point at the start of the graph, and the last point, that is 11.7 and 0.6. So 0.6 from the x-axis and 11.7 from the y-axis. So the formula is y2 minus y1 and x2 minus x1. So let's solve that. Okay, so 19.4, and this is one of the coordinates, and this is our other coordinate system, x coordinate points, x1, y1. So let's subtract them. 19.4 minus 11.7 and 0.1 minus 100 minus 0.600. Remember, you can't just switch it and do higher value minus lower value. You have to keep the symmetry. It's y2 minus y1 and x2 minus x1. Be careful with that. Okay, so let's solve that. So we get minus 15.4. That is the slope. And to find k would just be the negative slope. So minus of minus 15.4, that is positive 15.4. Right. I'm sorry, the graph is moving just alongside because it's annotated. Let's look at the last question, which is determine the value of resistivity from the graph. It's 3 marks. So we are provided with the diameter, and we got to find the resistivity. Let's go back to this part. Part I, it was about resistivity is equal to y-intercept times area. So from the graph, we'll find the y-intercept and we'll find the area separately, and then we'll multiply those two to get the resistivity. So let's find the y-intercept first. I'll adjust the graph right where it was. Okay. So we have to find the y-intercept. Now, you might be like, this graph is not touching the y-axis. So in that case, you will just extrapolate the graph. Okay, extrapolation is a technique where you extend the graph to see where it would touch a particular axis. This way you can find y-intercepts or x-intercepts. So let's extrapolate it. So again, we'll be drawing a line from this point, a straight line that would, like this line should exactly extend. So it extends up till here. This is about between 20.8 and 20.9. So about, but I think it's closer to 20.9. So yeah, let's just label this point. This is 20 point, this point. This is the y-intercept. It is 20.9. So we mentioned that down below. The y-intercept is 20.9. Remember to always look at the units of the graph carefully as well. This is ohms per meter. That is standard. Okay, there's nothing ambiguous about that, but you should always check the units. Now, to find the area, we were talking about a metal wire, right? And that metal wire had a diameter of 0.27 millimeters. Over here, I'm talking about. This is the diameter. So using this diameter, we can find the area. So the area of a wire, what is the formula for area? Area is just equal to pi r squared, right? We are provided with the diameter. Radius is diameter over 2. So it's d over 2 squared. So pi d squared over 4. So it was just 0.27, right? Yeah. Let's substitute the value here. 0.27 squared over 4. And it was in millimeters. See, very important point. It was 0.27 millimeters. So you have to convert that to meters. 1 millimeter equals 10 to the power minus 3 meters. So multiply it by 10 to the power minus 3 and then square. Okay, so I got 5.72 times 10 to the power minus 8 meters squared. That's the unit of area, meters squared. We'll substitute it back here in resistivity, 5.72 times 10 to the power minus 8. And that gives you 1.19 times 10 to the power minus 6 ohms meters. Why? Because that's the unit of resistivity. Resistivity's formula is resistance times area over length. So it's ohms meter squared over meter. That simplifies to ohms meter. So the correct unit. So this is the final answer for resistivity. So I hope that's clear, guys. And if you have any questions, please leave a comment below. Um, that's all. So happy learning. See you in the next video. Please like and subscribe. Bye.